How you doing? I've had my coffee. I got a lot to show you today. Going to start off with a little bit of what a developer advocate is. It's actually kind of a two-way position. We do outreach, which means that we come and we give presentations, workshops, etc. on what Google products can do. Try to get the information out there, making sure that the users that could make use of it are aware of it. And then the other direction is kind of like inreach. We find out what the communities need, the scientific communities, and what our tools really aren't doing a good job at. So that's a lot of why I come to these conferences and EGU and AGU and things like that, is to figure out how it should change our development in the future. There's, I guess, three things that I want to kind of convey today in this presentation. And the first one is just what is Earth Engine, this project that I primarily work on at Google. The second is how it's been used by external partners for their mission. And then a third is kind of just looking at what is happening in the future, or what is already available there but just hasn't been exploited in terms of the tech world. Some of the technologies that have been developed over the last few years that are really popular if you go to Silicon Valley, but not necessarily when you go to into some earth science community. So those are the three things that I'm going to touch on today. But to start off with, I wanted to put up this glamour shot of earth scientists working in the field. This is Niwot Ridge in Colorado. It's where the NSF has a long-term ecological research site. Green Lakes Valley is in the background. It's up about 12,000 feet. It's the main water supply for Boulder. It's highly instrumented, but I like this as an example of just a few things. One is it's really hard to get good quality reference data on the ground. And although we kind of always say, or it sometimes is referred to as ground truth, it's sometimes, or if you've collected it, you know that can be really a far thing from the truth, because you're out there, in this case, after you have slogged up 3 miles on skis and over rocks, and your hands are freezing and you're sweating, but then you stop in the cold, you have to fix wiring, and you have to maintain these equipments, and you have to get out data loggers out there. So it's just an example of all environmental data usually that's collected. It's messy in some ways. It has its own biases, its own quirks, things like that. But the other thing is that it's extremely valuable. This is where I started. Another reason I bring this up is I spent 4 years doing this before launching into my academic career and then going into Google, is working on this field site. And it's intensely valuable, this type of data, when you try to then bring in things like remote sensing and extrapolate it to the rest of the world. So you can't lose these kind of ground measurements, even though they are extremely messy to work with. But I'm assuming that a lot of people have kind of been in the field or tried to work with remote sensing data and field data, so you already kind of know this. Earth Engine is a tool that I wish I had as a graduate student. I wish I had was as a soft money research scientist at a university. Our goal is to kind of take away some of the painful things that you have to do in order to work with large amounts of data and make it much easier. But to explain what Earth Engine is, it's often useful to start off with what it's not. It's not Google Earth. Google Earth is the 3D globe that's been around for over a decade now. Over 1 billion people have downloaded it. Your 10-year-old kid can fly around the world and tell you great things about it. It's great. It's an outreach. It's a visualization tool. Earth Engine is it's an engine, it's a core that processes a lot of messy data like satellite data or climate model data. And one of the outputs can be images that could go on something like Google Earth, but it's very much focused on data processing. We view that Google Earth kind of, in some ways, revolutionized the idea of GIS, that you no longer had to be a technician. You could be a 10-year-old kid and work with satellite imagery in some ways, or at least explore it. We're trying to do the same thing with Earth Engine, but more for the analysis of data, which I would argue is a much harder problem than we had with Google Earth. So in summary, Google Earth Engine is a cloud platform, petabyte scale analysis of georeference data, and that can be satellite imagery, climate data, raster vector data. We try to build tools that make that easier. Kind of a core to this is that we bring all the data into one place and we take it off. We do data rescue in a sense. Pull it off of tape drives, put it onto hard drives in Google data centers, put algorithms that are used to analyze it next to it, and then give it access to like tens of thousands of computing cores at the same time, and then provide APIs for the outside world to take advantage of this. This is sort of how it looks like the service. If you can think of Earth Engine as kind of a black box, it has a lot of data sets in there, geospatial data sets. It has a lot of algorithmic primitives. We're up to about 1,000 of them right now, and we keep adding them as needed. Keep adding data sets as people come to us and say they want an additional spatial data set added there. And then it has a lot of computers in there. And it just sits there listening on the internet for requests about what it should do with this data and what do you want to get back, and then it sends back things. And that can be like an image, it can be a video, it can be a whole host of different results. It's not just images. The Earth Engine data catalog is pretty extensive. The biggest chunk of it right now is the Landsat Archive. We have over 5 million Landsat scenes on spinning disks, so you can have instant access to them. It's stored in the original projection, original bit depth with the band information, all of the metadata, and you can use that in your algorithm. So we're trying to preserve as much as possible the scientific data, but just store it in a way that makes it really fast to access. We set up pipelines for a lot of these different data providers, so we're just ingesting whatever they can provide nightly, like USGS. We are now pulling from the Sentinel Data Hub of ESA. And then there's other ones that are more static data sets in there, like high-resolution terrain data sets that aren't, that they're updated incrementally. And it's not just satellite imagery. We have like climate model forecast data, atmospheric weather prediction data from NOAA, et cetera. It just keeps adding as people say they want additional data sets. We figure out whether it fits into our system and bring it in and make it accessible. Earth Engine started as a, I guess, a .org project for philanthropic uses, and the main use case at the start was looking at deforestation in South America. There were people that were using Google Earth, and they could see with the time slider, that is, if you look back in time, forest was getting chopped down. You could visually see that, and they said, well, can't you make us a tool that we can actually analyze that rather than just looking at it? And so that was the start of Earth Engine in about 2009. And our goals are just to make the process of doing earth science faster, whether that's developing an algorithm or getting the information out to others. We're focused on removing barriers that can enable that to happen. We have a strong kind of ethic of like we will support people that have an open mindset so that they want to share their data, they want to share their code from the start, not just after it's been published. Those are the ones we want to work with because if we enable those people, those are the ones that we think we can get to scale the results because they will share those results with others and others can build upon it. One of the typical things, or at least when I was as a soft money researcher, I would go through this process of trying to have a hypothesis, and then you have to figure out what data you need in order to test it. If it's remote sensing data, often I don't have in here. Just write a proposal to get funding to actually do 1 to 3 years of work on this. But then you have to figure out like how you can set up the hardware, how can you download the data and put it in an organized way to test your hypothesis, and then finally code something up, process the data, and test. And if you're lucky, you get through that in your 1 to 3 year funding cycle because you have a lot of other things going on at the same time. In Earth Engine, we're trying to flip that a little bit and take care of the downloading the data on hardware that you don't have to maintain ahead of time, so that you can focus more on just creating a hypothesis and quickly testing it. And we want this cycle to be on the order of minutes, hours, days, not months and years in order to do this. So that's kind of our goal. I'm not going to talk much about Landsat because I'm sure that this is common information for everybody in this room. Although I'd like to say that if Landsat and USGS and Landsat didn't make the Landsat Archive free in 2008, I probably wouldn't be here talking about Earth Engine. It probably wouldn't exist. Basically, that was a driver when, in 2008, when it was released, we started the project in 2009 because there was a role that Google could fill. Basically taking all this large amounts of data, which Google is good at handling, and make tools to expose it to other people. So I'd like to thank USGS especially for my job right now. One thing that we do, especially with the Landsat Archive, is we help, I would say, USGS in a way distribute the data because they have limited capacity of spinning disks online in order to make it accessible to other people. We don't really have this limitation so much at Google, so what we've been doing is mirroring all of the images that USGS Eros has been exposing over the last 5 or more years. Anything they put up on their servers, we mirror so that people don't have to request it off of tape in the future, unless they change the processing algorithms. We put it in the data centers, we move aside like the Gmail and whatever else, search that's going on there. And it's a large amount of data in some sense, but for Google, it's a small amount of data. So nobody really cares at Google that we're doing this in terms of consuming resources, because we can have a lot of impact doing it. And then we make it available through an API like this. This is a JavaScript API. We have an equivalent Python API. Are there code? Who touches code, in the course of a week here? I think this is going to reach at least somebody in here. Okay. So I'm not going to have equations in this talk, but I have a little bit of code here. But I'll walk it through here. Actually, I'll go to the demo of Earth Engine running this code that you saw up there. And at the top there is a line that says, here's a collection. Give me all the Landsat 5 algorithms to top of atmosphere corrected. Filter it down to a particular year, 2001 to 2002, and then take the median of all the values of those overlapping scenes and finally add it to the map. So we got 4 commands that are up there and a bunch of comments. But the result is down here that you can now pan around wherever Landsat 5 was collected during that year, and if you want to change the year, it's pretty easy. You can change the visualization parameters. And this is, just 4 of the 1,000 of methods that we have available in our toolbox. These are just some of the more common ones. But there's all kinds of things that you would typically do in a remote sensing package or a GIS package with raster and vector data that's accessible. You can just do it at large scale. And kind of the nice thing about this is that as you're working on an algorithm, you get it for free, kind of implemented wherever the data is available. And so we can produce results quickly. You can produce terrible results really quickly too. So that reference data that I talked about is really key. And I think one of the key things we have to add to Earth Engine in the future is just make it easier to do the kind of cross-validation against reference data. Get statistics of how well you are doing when you produce a map like this. I was here yesterday for at least half of the day, and I sat in on the town hall in the evening, and I was intrigued by this picture of the algal bloom, so I had to, of course, go look for it as I was sitting in the back there and try to figure out what we could do with Earth Engine in here. So I made up a little demo here, and it illustrates a few more aspects of what we have available through this GUI interface, which is something that Google hosts and maintain. It's just one of the ways to access Earth Engine. We more try to encourage people to build their own user interfaces on the outside. But within, under 100 lines of code, I could get 4 linked maps in here. One is just giving you an overview on the left. There's one that's Landsat 8 data. There's one that's showing Sentinel-2 data. There's one that's showing MODIS for the same time. They're all linked together. And I was looking around, and it took me a little bit while to look through the Bering Sea, but I found that ship that they were talking about in there. And so you can see what it looks like in the MODIS over on the side, and Landsat didn't collect on that same day at the same time. But this is, it's a tool that you can be bored in a place with not really good Wi-Fi, listening to speakers and actually get work like this done. It's more what they're doing at the same time. I did want to point out that Landsat actually imaged a different part of the Bering Sea on that same day and had some really cool ghostly looking images at the same time. But anyway, this is what I do all the time when I'm sitting and have internet. So let me tell you, I guess, where this kind of fits into the whole kind of cloud technologies. And you can think of cloud services as ranging from infrastructure as a service. Those are things like Amazon Web Services, Google Cloud Platform, Azure, things like that. They're low level like storage, CPU, sometimes like some machine learning type of things, but it's pretty low level. You have to figure out how to chain them together. On the other end of the extreme is something like software at the service at the top. That's like Gmail. Everybody knows it just does email. It's very has a single purpose in mind, and it's kind of these categories are a little bit artificial. It kind of ranges from a high level of customability at the top or the bottom with the services to something like Gmail, which you still can customize a little bit, but It's more built-in functionality. Earth Engine is somewhere in between. It's what we think of as a platform. It's a platform for geo-reference data analysis. So some of the examples I was showing you in there. And what we do is expose, once again, the functionality as an API so that groups like WRI and Amazon and Brazil, they can build these websites that actually can access all of the georeference data and have their own kind of user interface for the world, depending on what their message is that they're trying to get out. People get access by just going to earthengine.google.com, clicking sign up and saying, hey, here's my name, here's my organization, and I want to do something. And that's kind of the barrier to entry. Well, we do read these things, so it takes a few days sometimes for us to actually get back in the office and read them. But that gives you free access for non-commercial use for the entire platform. If you do want to use it commercially, there is an option for that. We just have to have a discussion about what do you want to use it for. And we do have some commercial users, but they're a really small minority of our users. Most of our users are algorithm developers or NGOs that are building websites. Okay, this is nothing other than a break. So I actually wanted to say that that's kind of the introduction to what Earth Engine is, and if what you can take away from that is it's a lot of computers running or holding a lot of data on Earth and the ability to chain it up with some algorithms. That's kind of it at the core. So the next question is like, what have partners done with this? And we like to support the users that are going to have an impact on the world. And the way we go about evaluating that is there's different ways to have impact. One is just creating new knowledge. And I think that probably the audience here fits probably most strongly into that category. But we also have the idea of just raising awareness, just not generating the knowledge and putting it into a paper or something like that, but making the general public or decision makers aware of it. And if you can actually provide a tool that allows us as decision makers to actually take some action that has change, that's when we think we're really getting into real impact. So we like to get papers out. It's great, but it's just an intermediate step, I think, in terms of having real impact. We guide our development by basically what our users tell us. And one thing that came out recently was the UN Sustainable Development Goals, or at least a revision of those. And there's a lot of these align up with the community's action, or the communities that have been talking with us and what they're focused on. And I want to give you some examples from our forest vertical that fits, I think, into the life on land. And we worked with Matt Hansen of the University of Maryland and a bunch of his colleagues to help him create a global map of deforestation based off Landsat data. And so this resulted eventually in a science paper, but the processing was a lot of large numbers. And this is kind of neat because they're large in some ways, but on the other hand, nobody at Google really cares about them. It's kind of in the noise. So we can do this over and over again for other groups, which is the cool part about it. It resulted in a paper in Science. This was our first kind of high-profile paper that featured Earth Engine in it. And then I'm very excited that in addition to the paper, he allowed the data to be downloaded under a Creative Commons license so that other people could take advantage of it and build upon the results. And people did. So one of the main users of this has been WRI and their Global ForestWatch Collective. They have a consumer application called Global ForestWatch where people can actually draw on the map and say what went on, what are the statistics in this area, and explore a bunch of other different data sets kind of mashed up with the Global ForestWatch data set. It's just one of many in there. There just recently, or I guess in the last year, we did a partnership with Science to do their Science in the Classroom, a Science in the Classroom application. So it's kind of changing the user interface of that really detailed data set so that K through 12 students can explore, what's going on in these different countries. And it has like little quizzes in there about what caused deforestation here. Was it bugs? Was it sugarcane? I don't know. All kinds of different things in there. So that's another way of raising awareness. WRI has done a great job of outreach and actually conveying this information in a form to a bunch of different decision makers there. They document it on their website there. But just a few of the examples of the real world impact that we've seen from here is the Indonesian government utilizing Global ForestWatch data, that deforestation data, in law enforcement, so like who is setting the fires, are they actually allowed to, who owns that land, etc. It allows them to respond on this really large country that's many islands and really hard to get around on. It's useful for them to do monitoring. The next example I wanted to go through quickly is not Earth Engine focused so much, but it has to do with water, so I want to put it in here. We recently had an announcement of Global ForestWatch, and this is a project that is taking the world's data set of locations of vessel through this AIS system, transmitted by satellites or a bunch of other receivers, but they track, tens of thousands of boats, and this is, the opening day of fishing on some harbor in China. There's a lot of these things that you need to track, and it's millions of observations a day. So once again, we went through, created some knowledge, got a publication in Science in collaboration with SkyTruth and Oceana, and there's a website for raising awareness on this, where people can go in there and they can actually look at and track individual ships and see what their behavior is. And the neat thing about this is that when you can zone in on the movement of a particular ship like that, you can figure out what it's doing. You can figure out, they don't want to waste fuel unless they have a purpose. So you can figure out what type of fishing they're doing, whether they're meeting up with other boats, whether they're in exclusion zones, etc. So one thing this does is allows people to monitor, protected areas and what's going on. This is an example of that for a protected area that went in force, and you can see the ship tracks there just disappeared over the next year, so it seems to be working. Indonesia thinks it's so valuable that they are going to contribute their vessel monitoring system data, which is separate from the AIS data, into this database, so people can use that also for tracking fishing activity. It's been used in court of law to actually levy fines in the case of illegal fishing. And this was, a small fine of $2.2 million, but it's 1% of their GDP, so it's significant. And then my kid really likes this type of impact. It's like the Indonesian government is now blowing up ships of illegal fish that have been identified by this and posting them on YouTube. So as a warning, don't do this. So that's real world impact. Other things we do are a little bit more restrained. This is like a video that we created with Time magazine called Timelapse. It's just a true color representation based on Landsat, spans the course of 25 years. I think we expanded the years now. But it just allows you to zoom around the Earth and explore, kind of see what happened on a yearly time scale. This same technology, the ability to export videos, is something you can do through the API, and it doesn't have to be these true color representations. If you have a parameter of interest that you're generating over a time series from remote sensing imagery, that's one of our use cases for the API. It's something that we teach in our EE 101 class. It takes about 90 minutes to go through. So it's pretty basic functionality for Earth Engine, but it can be really impactful if you get it in the hands of the right people. All right, water. Let's focus a little bit more on water. This is a time lapse, or not a time lapse, I guess, a little shot in time of water droplet at San Francisco's Exploratorium, and yes, that is me in the background. I focus on water. My background is in civil and environmental engineering and geography, and I do the main support for Earth Engine that has to cover the water cycle. The water cycle is one of the 3 verticals that we have right now for Earth Engine, and our verticals are the areas that we focus our support in. So these are the conferences we go to, these are the high-touch partnerships that we establish, and so I work in the area of water. And they matched pretty nicely each of these verticals to the Sustainable Development Goals. But water, I would argue, actually matches to a lot of them, not just clean water and sanitation, but what is being produced and dumped into the waters, the lakes and waters, how are the forests changing and the wetlands that filter the water, how are the fisheries being impacted by this, and how is that going to change in the future. All of this is relevant to the work that you guys are doing here. In 2015 is sort of when we kicked off support for this water vertical, and the way we did it is we brought people to Google, about 25 experts that we picked from academia, governments, NGOs, tried to get at least a representation of the community so they could tell us what we should be doing. And we were looking for an overlap of like what needs to be done. Is there something that just needs to be scaled that Google could help with, and will it really change the world? These are the top areas of interest that came out of that meeting, and so I'm going to talk a little bit about there, but water quality in lakes and coastal zones was one of the important topics that seemed to come out of this meeting. And part of it is that I guess one more characteristic of whether it's successful is that we don't just have to find out that we could do something and there are interested parties, but is there actually somebody that's going to lead it and move forward? Because at Google Earth Engine, we get lots of requests to do stuff, and we are tool builders. We have to focus on that. We can't lead, I guess, any of these efforts. We can build cool tools, but Google is not going to do anything that you won't do yourself, basically, unless you convince us why. But do it yourself. It's a lot easier to do so. One of the main water products that is coming out in terms of like generating knowledge, it's in peer review right now, is a map of the world based on Landsat data from the last 25 years with monthly statistics of whether there is water expected there or not, based on the Historical Imagery Archive. This comes out of the European Commission Joint Research Center. Another similar one, it was looking for surface water changes over that time period, but not on a monthly scale, just looking whether there's been a trend towards water gain, land gain, loss, etc., that you can go and explore here. And this guy, Genna, did an awesome job of just coding up a website on his own. How many students are here? I missed that yesterday when there was raising up their, like 10% or something like this. So Nature Climate Change publication website being used around the world, he's a grad student. He's a really smart grad student, but he's just a grad student making use of the tools to do things like this. Work of another grad student, Alex Brick, he's a PhD student at the University of California, Berkeley, is looking at Landsat data in terms of erosion deposition, so fluvial geomorphology kind of research. And he is starting to disprove some of the long-held truths, I guess, of geomorphology. When you look at like 40 years of data, you can show things don't really work the way that they might have been described in the textbook. And so he not only starts with the Landsat Archive, but he's been using our API in very creative ways to figure out what the river widths are, figure out when erosion happened, deposition happened, etc. Really interesting work that he's done there. All right, another break. How am I doing? Okay, 12 minutes. Home stretch. All right, so what's on the horizon next? A lot more of what we've been doing. I think a lot of the work that we've been doing in water is going to eventually amount into these global systems for looking at land cover change, land use change, especially as it relates to water use. Evapotranspiration services is pretty key to that, trying to monitor agricultural fields, figure out how much water that they're using. And then there is work in the area of global floods, knowing what flooded in the past, kind of the history of it, so we can eventually make predictive services of there. A lot of these are, right now we can do this, we just have no idea how well we are doing this. So the whole idea of like building in that, those metrics of being able to tell yourself how well your model that you created is doing is just key. Because, yeah, got a hard time on that one for a while. There are several groups that are looking at monitoring where are the agricultural lands, what is their predicted yield. A lot of this is tested in the United States where we have good data, but the real applications are in places like Africa, which the fields are harder to find, and the results are much more crucial in terms of like what is the food production for figuring out where aid has to be sent. As I said, we have people that are working on evapotranspiration. This to me is fascinating because it doesn't just take like optical data, but it takes weather data and digital elevation models to come up with measurements of how estimates of how the winds are transferring water off of the plants. So it's a multi-sensor data fusion in order to make this go, and we're trying to do this at a global scale too, from a variety of different algorithms. Another thing that I think is really important in coming along the pipes is algorithms that don't depend on a single sensor. We need to move into more of the realm where there is something we're trying to estimate that's continuous in space and time, and we just have these sparse observations of it. And they're sparse spatially, temporally, spectrally, and probably a bunch of other characteristics in there. So the uncertainties are going to vary depending on the data that you have, but that's just reality. And I think that we have to move away from this like single sensor type of algorithm development. I think Earth Engine can take away a lot of that pain because we can do things like reprojection on the fly, almost instantaneously, like the examples I've shown you before. There's going to be a need for a feedback loop of like ground reference data collection that can immediately inform models and get results back to the users. There's an open source project called Open Data Kit, and they have, works on Android smartphones. You can design a form that can take pictures, you can record bird sounds and things like that. You can send that off to the cloud when you get back to a cell network. That can be ingested into Earth Engine as reference data that can be used to train models that are put on a website instantly. I think this round trip can be under a minute, basically, from somebody collecting something in the field, as long as they can figure out a way to transfer it, that we can get back an updated model to them. So that's a loop I think is very exciting. Another one that's exciting is this idea of deep learning. That we're okay, at creating these deterministic models about how things should work, but there's always some error that we can't explain. We're limited in terms of our understanding of how things work physically, or we just have noise in the system, the sensor or something else is causing it. I think that these kind of deep learning techniques can be used to figure out how to deal with that noise, even if we don't fully understand it. So I'd see a way that we're doing a lot more work on Earth observation data, not just with things like random forest classifiers or CART or support vector machines, but this is kind of like the next iteration of that. You can move to these deep neural nets to really exploit, once again, when you have lots of data that is available. All right, back to Victoria. And you gave me the soapbox up here, so I have 8 minutes to tell you what you should be doing. So once again, who is still on the learning path out here? And that better be more than the students. Okay, so coming from the tech world in Silicon Valley, if you don't know what these things are, take a month of your time and learn them in detail, especially like GitHub, and use them. It makes your life so much easier. I wish I had this when I was a grad student. I could actually go back and do my analysis that I did as a grad student. Right now it's locked away in a paper and I'm the author. I can't even go back and do it easily. But these technologies are all about sharing data. Docker is for spinning things up on your laptop that can be instantly translated to data centers and run on thousands of machines. Python is Python. Jupyter is a web notebook that can embed both code and annotations, so you can actually teach entire lessons in like one web page. It's fascinating, comes out of the University of California. Berkeley is one of the main drivers of that, but it's supported by the Moore Foundation and the Sloan Foundation to the tune of millions of dollars in support of the Jupyter project. It's awesome. Figshare is just a convenient way to make your data accessible, because it's really hard to, if you think somebody's going to come to your particular website to access code or data, you might reach a small community, but if you put it on GitHub or Figshare or something, you just are going to increase that by orders of magnitude. And Software Carpentry is a group that goes and they teach how to use these technologies, the key ones, for scientists. So it's awesome. They're free. They have free lessons online, or if you have enough interest, an instructor will come to your organization and teach you about these technologies. So take advantage of that. The other one is, I really want to emphasize, to move science forward quickly and to have impact, we need to promote and really follow these practices of open science. And don't wait until your paper is submitted and that your funding has run out before you dump it on some site and call that as being open with your results. Do it from the start of your project. Have your developers working on GitHub in the open. And I know that there are disincentives to doing this, at least that are voiced quite often, but the benefits of that can be huge. You can get all these people that you don't know contributing your site, using your stuff, because it's not just that you're collecting data and building algorithms. I'd argue that the real value is actually if you have impact, and if you're successful at that, you can get your rewards from whatever organization that you're in. It's not just citations. There's all other things that could be argued that are very valuable. And then finally, I think that just for this community itself, I mean, there's a lot of these algorithms that I'm hearing about and the detailed science and the equations that you put up there that could be put into a form that would just make it easy for people to work with. So this is an algal bloom, early version of an algal bloom detection algorithm by researchers at Carnegie Institute for Science. And this is on Earth Engine. You know, once you put it in there, they developed it for Lake Erie, you can start extrapolating to areas that it doesn't make sense to, but at least it's a platform that you can start figuring out why it doesn't make sense. When does it not work? You know, if you go over to the Caspian Sea, is this algorithm still working? Can identify areas where it's having a problem. So I think that there's a lot of stuff that I'm hearing from the presentations in here that is reaching the level of maturity that you should think about how do you scale it up and bring more awareness into it. So that's, I guess, my main take home there is that we're here to try to help you move from that knowledge, the valuable knowledge that you're generating, the data that you're collecting, to make it so the world can actually take advantage of it. So take advantage of us and the other groups in Silicon Valley because we just like interesting problems to work on. So thank you.
We have time for questions.
I like these cubes. We have to get some of these at Google.
Hello. Well, thank you very much for this fresh breeze of new ideas and new technologies. We've been doing data science for even before the word data science had been done, and now the business world is going at it.